Hello. In the previous lecture, we were proving the following result about Noetherian modules. Similar to rings, where we showed a ring is Noetherian if and only if every ideal is finitely generated. Next, we want to show that every module is Noetherian if and only if every submodule is finitely generated. We have already proved that if M is Noetherian, then every submodule is finitely generated. Next, we want to show the other way around, the converse. Assuming that all the submodules are finitely generated, we want to show that there is no strictly ascending chain of modules, submodules. So we start with a chain of ascending submodules, m sub 0 contained in some m sub 1, m sub 1 inside m sub 2, and so on. And we want to show that from some point on, we are getting the same submodules. So as before, whenever we have a chain of objects, algebraic objects, then when we take the union of this chain, we should get a similar structure. So if we take a chain of submodules, then the union of this chain should be a submodule as well. So that would be our first step. Let N be the union of this chain of submodules, and we want to show that this N is a submodule of M itself. So that's our claim. What does that mean? This means we need to show that N is a subgroup of M, is an abelian subgroup, and it is closed under a scalar multiplication. Let's start with why it is a subgroup. Actually, at the same time, we can also argue why it is closed under a scalar multiplication. So let's pick two elements, n and n prime, in capital N. I need to show that n minus n prime is inside capital N, and at the same time, r times n for every r inside the ring capital R is still inside capital N. Okay, let's start with understanding what it means that n and n prime are inside capital N. Capital N is union of these m sub i's. Saying that n is inside capital N means I can find some index such that n belongs to m sub I. Saying that n prime is inside capital N means I can find possibly a different index where n prime belongs to m sub j. Now, here is the place that we use the fact that m sub i's form a chain. So either I is at most j or j is at most I. Without loss of generality, I can assume that I is at most j, which means m sub I is a subset of m sub j. Now, that means both n and n prime are elements of m sub j. Because m sub j is a submodule, it's a subgroup in particular, n minus n prime belongs to m sub j. Because it's a submodule, r times n is also inside m sub j, no matter what r is. Altogether, notice that m sub j is itself as a subset of capital N. We deduce that both n minus n prime and r times n are in capital N, which shows that capital N is an abelian subgroup and it is closed under scalar multiplication, which together imply that N is a submodule. Now, what do we know about submodules? The assumption is that every submodule of M is supposed to be, every submodule is supposed to be finitely generated. In particular, this capital N should be finitely generated. So suppose this submodule is generated by elements n sub 1, n sub 2, n sub k. Again, n is union of m sub i's. Knowing that n sub I belongs is union of m sub i's. Knowing that n sub I belongs to n implies that this n sub I should belong to m sub some index. The index, of course, depends on I, so let's call it r sub I. So n sub I should belong to m sub r sub I. Now again, we want to use the fact that m sub j's form a chain. If I take the largest index among r sub i's, then that index, m sub that index, contains all the other involved submodules. In particular, that m sub r contains n sub 1, n sub 2, dot, 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 n sub k. So that's what we do. So let's take r to be the max of these indices, and then use the fact that m sub j's form a chain and deduce that m sub r sub I is a submodule of m sub r. Knowing that n sub I belongs to m sub r sub I and this is a submodule of m sub r, we deduce that all n sub 1, all these elements, n sub 1, n sub 2, dot, 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 n sub k, are elements of m sub r. And that means the module generated by these elements is a submodule of m sub r. But remember, the module generated by n sub i's is capital N, which is union of all the elements inside this chain, which means this union is a subset of m sub r. Now, what does that imply? It says that for every I that is at least r, m sub I is a subset. Okay, so this implies that for every I, m sub I is a subset of m sub r. But if I is at least r, I have the other way around as well, because m sub j's form a chain, and when I is at least r, we also have that m sub I contains m sub r. So we get both sides of these inclusions, which means that starting from index r, we are getting the same module. And that's exactly what we wanted to show. We wanted to say that every ascending chain of submodules would stop at some point. So that implies that M is Noetherian. Okay, so far we have a description of Noetherian modules in terms of finite generatedness of its submodules. But maybe it's not good enough from a structural point of view. It doesn't give us a constructive way of understanding what modules are Noetherian. So we cannot produce many modules that are Noetherian using the previous proposition. But the next proposition is an extremely important tool for us to construct many Noetherian modules. Okay, what is this statement? So suppose that I'm giving you 3 submodules of a given module M, and B itself is a submodule of A as well. Then the module A is Noetherian if and only if its submodule and the quotient of A by that submodule are Noetherian. So whenever I give you a module and a submodule of this, if this guy is Noetherian, then all the submodules are Noetherian, all the quotients are Noetherian. And the interesting thing is that the converse is kind of true as well. So in fact, if I give you a submodule and I tell you that it is Noetherian, and the quotient of my module by this submodule is also Noetherian, I can deduce that the original module is Noetherian. So in the case of vector spaces, it's similar to saying that if V has a subspace W, a finite dimension, and V over W has also finite dimension, then V itself is of finite dimension. Now, the second part says that if A and C, if I give you two submodules of a given module, if both of them are Noetherian, then so is A plus C. Of course, the converse is true as well, because A and C, both of them are submodules of A plus C. If I tell you that A plus C is Noetherian, then you can deduce that its submodules are Noetherian, and that means you can deduce, you can conclude that A and C both are Noetherian. So the second part can be also written as an if and only if statement. Okay, let's start with the first part. Let's assume that A is Noetherian. I want to show that both B and A over B are Noetherian. Knowing that A is Noetherian, I can deduce that every submodule of A is finitely generated. This is what we proved in the previous proposition. Now I want to use the same proposition to show B is Noetherian. That proposition tells me in order to show that B is Noetherian, it's enough to discuss why every submodule of B is finitely generated. But notice, every submodule of B is also a submodule of A. Because submodules of A are finitely generated, we can deduce that every submodule of B is finitely generated. And therefore, by the previous result, by the previous proposition, we can deduce that B is Noetherian. Okay, now let's see how we can show A over B is Noetherian. In order to understand whether or not A over B is Noetherian, we need to have an understanding of its submodules. In the case of groups or quotients of rings, we have seen a kind of correspondence result. In the case of groups, we proved that when I look at a quotient group, G over N, then there is a bijection between subgroups of G over N and intermediate subgroups of G that contains N. Now we have a similar result for modules. No, not for Noetherian. It has nothing to do with Noetherian. This is true for every quotient of modules. So let's start with stating and proving a correspondence result for submodules of A over B. So this claim says that there is a bijection between submodules of A over B and submodules of A that contain B. So we are here looking for submodules or intermediate modules between B and A, and on the other side we have submodules of A over B. And what is the map? Similar to the group case, starting with A prime, I can just send it to quotient of A prime by B. Notice that A prime contains B as a submodule, and it does make sense to talk about quotient of A prime by B, and at the same time, because A prime is a submodule of A prime over B would be a submodule of A over B. So it is a well-defined function. What we want to show is that it is a bijection. Okay, so let's start by arguing why it is injective. If you think about it, at the level of groups, we have proved this kind of bijection. So, and that's exactly the same type of map. So what I'm saying is that in the case of groups, we showed that instead of submodule, if I replace this by abelian subgroup, then this map would be injective, and the image of this map would be not submodules, but rather subgroups of A over B. But the injectivity doesn't change if as I impose more condition on the domain. So that means the group theory part of the statement, the group theory result that we have already mentioned on the correspondence of subgroups of a quotient group implies injectivity of this function. So we get that this function is indeed an injective function. Now we want to argue why it is surjective. So we start with a submodule, A prime bar, of A over B. Again, from group theory, we know that A prime bar is of the form A prime over B, where A prime itself is an intermediate subgroup. So A prime bar from group theory is of the form A prime over B, where A prime is a submodule of A which contains B. Now, A prime is a subgroup. I want to show that A prime is a submodule. It remains to show that A prime is closed under a scalar multiplication. So that means I need to pick some element of A prime and a scalar, and I have to show that R times A prime belongs to capital A prime. But what do I know about A prime? By assumption, every coset that's represented by an element of A prime belongs to the submodule A prime bar. So that means A prime plus B belongs to the submodule A prime bar. Being in the submodule implies that when I multiply it by a scalar r, I am still inside that submodule. So r times A prime plus B is still inside the submodule A prime bar. The way that we define scalar multiplication in quotient modules is by multiplying only the coset representative. So this scalar multiplication is the coset that's represented by r times A prime. And that is supposed to belong to A prime bar, and A prime bar is A prime over B. So this coset belongs to A prime over B, which means that this coset representative belongs to A prime. So r times A prime is inside A prime, and that's exactly what we wanted to show. Altogether, we deduce that if A prime belongs to capital A prime and R is a scalar, is an element of the ring, then R times A prime is still inside A prime. Altogether, we deduce that A prime is a submodule, which shows surjectivity of this function, and that completes the proof of the claim. Okay, now that we have an understanding of submodules of A over B, we go back to what we wanted to show. We want to show that A over B is Noetherian. By the previous proposition, it is enough to argue why every submodule of A over B is finitely generated. So I am going to pick a submodule, A prime bar, of A over B, and I have to show that it is finitely generated. But what do I know about submodules of A over B? We have just showed that A prime bar is of the form A prime over B, where A prime itself is a submodule of A. Now, I know A is Noetherian. That implies that A prime is finitely generated. Recall that a ring is a module is Noetherian if and only if every submodule is finitely generated. Knowing that capital A is Noetherian, we can deduce that A prime is finitely generated. That means so we can find some generators for this submodule. Let's call them A sub I prime, and write down every element of A prime as an R linear combination of these generators. So every element of A prime is of the form sigma R sub I A sub I primes as R sub I range, R sub i's range in the ring capital R. Now, when I pass to the quotient of A prime to get A prime bar, we still see that every coset is a linear combination of AI primes, and by the definition of a scalar multiplication in the quotient, we see that every element of this quotient is an R linear combination of the cosets that are represented by a sub I primes. And that implies that this module is generated by these finitely many cosets, which means this quotient is also finitely generated. So altogether, we deduce that every submodule of A over B is finitely generated, and therefore A over B is a Noetherian module. Okay, so we prove that if A is Noetherian, then both B, every submodule, and A over B, every quotient, is Noetherian. Now, we want to prove the other way around. That means I'm going to assume that both B and A over B are Noetherian, and I want to show that A is Noetherian. That means, again, by the previous proposition, it's enough to argue why every submodule of A is finitely generated. So I pick a submodule, capital N, of A, and I want to show that it is finitely generated. But what is my assumption? The assumption that we have is about B and A over B. These are the blocks that we have. So we are going to split N, so to speak, into two parts and deal with them separately. So one part is the part that N has in common with B. So N intersection B, that would be a submodule of B. And the other one is the shadow, is the quotient of N by B. So if P sub B is the quotient map, I can apply P sub B to N, and then I get a submodule of A over B. As we have discussed, image of module homomorphisms are always submodules. P sub B restricted to N is still a module homomorphism, and image of P sub B restricted to N would be a submodule of A over B of the codomain. So P sub B of N is a submodule of A over B. But notice, what is P sub B of N? P sub B of N consists of cosets that can be represented by N. That means it consists of cosets in N of N plus B over B. Again, we have seen this type of result in groups whenever we give a quotient map from a group to its quotient and apply it to a subgroup, we get quotient of the normal subgroup times here, and the operation is plus the subgroup that we have applied to. So again, think about this equation. It's rather easy to see that P sub B of N equals to N plus B over B. Now, starting with a submodule N of A, we get these two submodules, one of them a submodule of A over B, and the other one a submodule of B. Our hypothesis says that A over B is Noetherian and B is Noetherian. Therefore, every submodule of A over B and every submodule of B are Noetherian. Therefore, both N plus B over B and N intersection B are finitely generated modules. Because every coset here can be represented by some element inside N, I can pick my generators to be represented by elements inside. I can choose my generators to be represented by elements inside N. So let's say the coset N sub 1 plus B, N sub 2 plus B, N sub K plus B. Now, suppose that this is a set of generators of this module N plus B over B. And let's pick a set of generators for this intersection. Because again, B is Noetherian and intersection B is supposed to be a finitely generated module. So I can find N sub 1 prime, N sub 2 prime, N sub L prime inside the submodule capital N. So that the module generated by N sub i's is precisely the intersection of n and b. Next, what I want to prove is that if I pick these n sub I primes and these coset representatives, then the module generated by them is the entire n. We have already chosen them in a way that they belong to capital N, so it's not surprising that the module generated by n sub i's and n sub I primes is a submodule of n prime. We want to prove the other way around, so that's the claim. Claim is that n is the module generated by n sub i's and n sub I primes. As I have pointed out, we have already chose these generators in a way that n prime is a submodule of n. Now we want to show the other way around. Let's pick an element inside the module capital N. I want to prove that it belongs to n prime. That means I need to show that it can be written as an R-linear combination of n sub i's and n sub I primes. We start with a shadow of n mod b and try to generate it using these generators n sub i's and n sub I primes. When I look at the shadow, that means n plus b, I get a coset in the quotient of n plus b by b. We know that this quotient is generated by the coset representatives, by the cosets that are represented by n sub i's. That means n plus b can be written as an R-linear combination of the cosets n sub 1 plus b, n sub 2 plus b, n sub k plus b. So the coset n plus b is r sub 1 times the n sub 1 plus b, r sub 2 times n sub 2 plus b, till r sub k times n sub k plus b. The way that we define the scalar multiplication in quotients is by multiplying the coset representatives, and the way that we add them is by adding the coset representatives. So altogether, we are taking our linear combination of the coset representatives n sub i's and then looking at the coset that they represent. I mean, this linear combination represents. So n and this linear combination represent the same coset mod b. That's the same as saying that the difference of the n and this linear combination is an element of b. So n minus this linear combination is inside b. But notice n and n sub i's, all of them belong to the submodule capital N. And therefore, this linear combination is also inside the module capital N. It is inside b, it is inside capital N, so altogether we deduce that this is an element of the intersection. So n minus the linear combination of n sub i's is an element of n intersection with b. But this intersection itself is generated by n sub I primes, which means this element can be written as an R-linear combination of n sub I primes. So I can find some coefficients, some elements of the module of the ring capital R, let's call them R sub j primes, and write down this difference as R sub j prime times n sub j prime summation of those elements. Bringing this element to the other side, we deduce that n can be written as an R-linear combination of n sub i's and n sub j primes. That means that n belongs to the module generated by these elements that we called n prime. And that just shows the claim. We prove that every element of the module capital N belongs to the module n prime. And we had already showed and discussed that n prime is a submodule of n. Altogether, we are done. We show equality, and that implies that the submodule n is finitely generated. And that is true for every submodule of the module A, and therefore A is Noetherian. Okay, so we proved that every submodule of A is finitely generated. We deduced that if B and A over B are Noetherian, then A is Noetherian. Next, we want to show that if A and C are Noetherian, then their summation is Noetherian. Okay, so the claim is so we want to prove that A plus C is Noetherian, and the technique is to use part A and kind of split A plus C into two parts. We know that C is Noetherian. If I show A plus C over C is Noetherian, we can deduce that A plus C is Noetherian. So we look at the quotient map from the module M to the quotient of M by the submodule C, and we restrict it to A. When I restrict it to A, I get that PC of A is A plus C over C. We had this kind of discussion in part A as well. Let me quickly go over the argument. This consists of the cosets that are represented by some element of the module A, and that means I can add whatever I want from the submodule C, and I get that all the cosets that can be represented by an element of A plus C belong to this image. And of course, because A plus C contains C as a submodule, that is precisely the quotient of A plus C by the submodule C. And this restriction is a module homomorphism. It's a surjective module homomorphism. And from here, we can use the first isomorphism theorem and deduce that A, the domain modeled by the kernel of the quotient map, is isomorphic to the image, and we just discussed that the image is the entire codomain. But what is kernel of this map? When I look at the kernel, it should belong to the kernel of the quotient map, which is C, and it should also belong to the submodule A. It should belong to the domain. And that means that kernel of this restriction is nothing but C intersected A. Altogether, we get that A modeled by A intersection C is isomorphic to A plus C over C. Now, we know A is Noetherian. By part 1, we know that if a module is Noetherian, then every quotient of that module is Noetherian. In particular, A over A intersection C is a Noetherian module. Now, A over A intersection C is Noetherian, and it is isomorphic to A plus C over C. So from here, we can deduce that A plus C over C is a Noetherian module. C is Noetherian. A plus C over C is Noetherian. Therefore, again, if we use part A, we can deduce that A plus C itself is Noetherian, and that completes proof of this theorem. Now, this proposition gives us many examples of Noetherian modules. The following theorem is a good indication of the strengths of this result. We have already discussed that a ring R as an R module is Noetherian if and only if the ring R itself is Noetherian as a ring. Now we see that this kind of, as soon as I tell you the ring R itself is a Noetherian ring, then every finitely generated R module is Noetherian. Not only R itself, which is the easiest R module that you can think of, maybe not the most easiest, 0 is the easiest, but one of the easiest R module that you can think of. From there, you can deduce that every a finitely generated R module is Noetherian. Okay, so again, if R is Noetherian, then every finitely generated R module is Noetherian. Okay, so let's see how the proof goes. And at the beginning of the proof, we also produce a kind of claim that's going to play an important role later when we want to classify finitely generated modules over certain rings. Okay, so M is finitely generated. That means that I can generate M by finitely many elements. So suppose M sub 1 dot 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 M sub M is a generating set for M. Now I want to argue that M is Noetherian. But what does that mean, that it is generated by M sub i's? It means that every element of M is an R-linear combination of M sub 1, M sub 2, M sub n. Now let's consider the following function from the Cartesian product of R to M. So I give you an n tuple of elements inside the ring capital R, and you give me back exactly this linear combination. So saying that every element of capital M is of this form implies that this f is definitely surjective, a surjective function. Next, we show that it is a surjective R-module homomorphism. So we need to show that f preserves addition and f preserves scalar multiplication. Both of them are rather easy, but let's check them quickly. So f of R1 dot dot Rn plus f of R primes equals to what? So the first one is the R linear combinations, R sub I linear combination of M sub i's. The second one, R sub I prime linear combination of M sub i's. I can reorder the terms, it's an abelian group. I bring the similar indices close to each other. I use the distribution property of a scalar multiplications on the module side and write this as R sub I plus R sub I prime times M sub I. But this means, if you think about it, this means that I'm looking at linear combination of M sub i's with coefficients R sub I plus R sub I primes. That means that it is f of the vector that's given by R sub I plus R sub I primes. And this is the summation of these two n tuples. So that's exactly what we wanted to show. We end up showing that f preserves addition. Now let's see why it preserves a scalar multiplication. So f of R times this n tuple is what? What does R times this n tuple mean? It means I need to multiply R by every component separately. So it is f of R times R1, R times R2, R times R3, and so on. But what does that mean? This means I need to take linear combination of M sub I with the coefficients that are given here. So I get this summation. Now I can use the fact that multiplication in the ring is compatible with module scalar multiplication and write down this scalar multiplication as a consecutive scalar multiplications, once by R sub I and next by R. Now again, I can use the distribution property of a scalar multiplication on this time on the module side, the other time it was on the ring side. So I can factor out R, and I get that it is R times this linear combination. This linear combination is nothing but f of R1 dot dot Rn, and that's exactly what we wanted to show. So altogether, we get the following statement, that if M is finitely generated, if M is generated by n elements, then there is a surjective R-module homomorphism from R to the n to M. Okay, that's a key kind of result that we are going to use later as well. So in particular, we deduce, using the first isomorphism theorem, that every finitely generated module is isomorphic to a quotient of R to the n for some non-negative integer n. Now, because R is Noetherian, I claim that R to the n is Noetherian, from which I can deduce that every quotient of R to the n is Noetherian, and that means M is Noetherian. This is how we want to show that M is Noetherian. Okay, so how do I know that R to the n is Noetherian? I'm going to think about R to the n as summation of n copies of R. What are the n copies? I put R in the ith component and put zeros in the rest of the components. And this is clearly a submodule of R to the n. Now, when I add all these submodules, I end up getting the entire R to the n. So R to the n is nothing but summation of n sub i's. And every n sub I is isomorphic to R as an R module. Now we know R is Noetherian as a ring, but we have discussed that if R is Noetherian as a ring, then R is a Noetherian R module. So R is a Noetherian R module. That means n sub i's are Noetherian R modules. By the previous proposition, whenever I give you finitely many Noetherian submodules, I can add them together and end up getting another Noetherian submodule. We showed this for 2 submodules, but then you can prove this by induction for every finitely many submodules. So n sub 1 plus n sub 2 plus n sub 3 plus n sub n is a Noetherian submodule of R to the n, but that's the entire R to the n. So that means R to the n is a Noetherian R module, as we claimed. Now it's a Noetherian R module. By the previous proposition, we deduced that every quotient is Noetherian, so R to the n over the kernel of f is Noetherian, and that implies that M is Noetherian. So we proved that if R is a Noetherian ring, then every finitely generated R module is Noetherian. In particular, if I start with a PID, principal ideal domain, then every ideal is not only finitely generated, but in fact every ideal is principal. So that implies that D is a Noetherian ring. Therefore, every finitely generated D module is Noetherian by the previous theorem. So at least now we have this finite generatedness. So finite generatedness implies Noetherian statement for every D modules when D is a PID. Okay, so now what? What next? We want to see what we can actually say about the structure of finitely generated modules now that we have this kind of Noetherian understanding of this finite generatedness. We can use this finite generatedness of finite generatedness implying Noetherian to give a concrete connection between finitely generated modules and system of linear equations. Okay, so let's see how we can do this. So suppose I give you a Noetherian ring and a finitely generated R module, M. My claim is that then M is isomorphic to R to the n. So we have already discussed that every finitely generated module is isomorphic to a quotient of R to the n. But now I want to describe it in terms of certain matrices. So the claim is that I can always find a matrix not necessarily a square matrix, a rectangular matrix, and M would be isomorphic to R to the n modeled by image of this matrix. What is image of a matrix? It simply means that I multiply A by column vectors, and whatever I get, that collection I call image of this. So you can also think about a matrix similar to vector spaces. You can think about this matrix as a linear transformation, as an R module homomorphism from R to the m to R to the n. And then in that sense, image is a submodule of R to the n. And we are modding out R to the n by this image. And the claim is you can always find such a matrix and write down M as a quotient of R to the n by the image of this matrix. So this quotient is sometimes called the co-image of this matrix. So we have image, and then we are looking at the co-image of this matrix. So the claim is that if I give you a Noetherian ring, a finitely generated module is always isomorphic to co-image of some matrix. Okay, let's see how the proof goes. We have already discussed, okay, so the assumption is that M is finitely generated, and we have already discussed that whenever I give you a finitely generated ring, you have a surjective R module homomorphism from R to the n to M, and therefore M is isomorphic to R to the n modeled by the kernel of F. Okay, so far we have used the first isomorphism theorem and the discussion that we had in the previous proposition. Now we need to understand kernel of F better. What we know is that R is Noetherian, and R to the n is a finitely generated R to the n is a finitely generated R module, and therefore by the previous proposition R to the n, by the previous theorem, R to the n is Noetherian. That means every submodule of R to the n is a finitely generated R module. In particular, kernel of F is a finitely generated R module. So kernel of F is a finitely generated R module. So suppose that kernel of F is an R span of V sub I. So suppose kernel of F can be generated by V1, V2, V sub M. That means kernel of F, every element of kernel of F is R times V1 plus R times V2 plus R times V sub M. So I can write it as an R linear combination of V sub i's. So that exactly means that kernel of F is the image of the matrix which consists of V sub i's. So where V sub i's are the columns of this matrix. Notice that when I multiply this matrix by x1 x sub m, I get x1 times v1, x2 times v2, xm times vm. I get an R linear combination of v sub i's and vice versa. If something is inside the image, it is an R linear combination of v sub i's. So then image of this matrix is precisely the kernel of F, and coupled with this isomorphism theorem, we get the claim that every finitely generated R module is isomorphic to co-image of a matrix, assuming that R is a Noetherian ring. Okay, so that means in order to understand finitely generated R modules, we need to understand co-image of matrices. What does that mean? In order to understand co-image of matrices, we need to understand image of matrices. What does that mean? B belongs to image of M, image of a matrix, image of A, if and only if this system of equations has a solution. So this brings us to system of equations. We need to understand whether or not AX equals to B has a solution in R to the M. Okay, so now how did we do this? How did we answer this type of question when R was a field or complex numbers? Our main tool has been the Gauss-Jordan elimination process. And we have already mentioned in the previous lecture that for an arbitrary ring, we cannot expect to be able to go through the same process. For instance, even if I have only one equation and one variable and have the equation ax equals to b, then where small a belongs to is an element of the ring and small b is an element of the ring, this equation has a solution if and only if b is a multiple of a, if and only if b belongs to the ideal generated by a. So it is clear that the structure of ideals of this ring play an important role in this question. And the easiest rings from the structure of ideals point of view after fields are Euclidean domains. So that's going to be our standing assumption. We are going to assume that my ring from this point on in this lecture is a Euclidean domain, and I'm going to denote it by D. And I try to go through the Gauss-Jordan elimination process and see how far we can get. Okay, so let's recall what was this Gauss-Jordan elimination process. So in the Gauss-Jordan elimination process, we had row reduction operations and column reduction operations. So let's recall what they were. We could multiply a row by some scalar and add it to another row, but do not change the rest of the rows. We could also swap the ith row with the jth row. We can do the same with columns. I put primes in order to indicate operations on the columns. So we can multiply the jth column by some scalar and then add it to the ith column. Or I can swap the ith and the jth columns. Let's notice that we can do these operations by matrix multiplications. So the E sub ij parentheses r operation, when we multiply the jth row by r and then add it to the ith row, it's like this, right? So what I'm doing, I'm changing the ith row, and instead of a sub I, I'm writing a sub I plus r a sub j. But this is precisely multiplying the matrix where every component is, so I have only the identity matrix, and then I add one component at the r I j entry. The rest of the entries of diagonal are 0, and here I have r. Then you multiply this matrix with the matrix a sub 1 a sub m. If you think about it, here the only row that's going to change is the ith row. So the ith row times this. So I have to multiply this 1 by a sub I and then r by a sub j, and end up getting exactly what we have over here. And the rest of the rows do not change at all. So these row operation can be represented by this matrix multiplication. I'm going to denote this matrix by E sub ij parentheses r. So this is an m by m matrix. Now swapping is again the same, so it's a kind of permutation matrix. And here this permutation matrix, everywhere I have identity except I'm swapping the ith and jth position. I'm swapping the I1s and put them in off diagonal. And when you multiply this by the matrix a sub 1 a sub m, you get exactly the swapping result that we are looking for. I can do the same for matrices. So here the permutation matrix I denoted by small s sub ij. When I do with columns, I will end up again the same matrix multiplication, but this time as matrices are multiplied from right. For rows, we had to multiply them from left. For columns, we have to multiply them from right. And it's a similar kind of elementary matrix. So this type of matrices are called elementary matrices. So again, it's going to be multiplication by some elementary matrix. And for swapping, it's going to be a multiplication by a similar permutation matrix. So altogether, we got these kind of matrices that we are multiplying by our original matrix to get from one to another, to run through these row and column reduction process operations. Let's also point out that when I take these elementary matrices, when I pick the same entry, ij, so R, I put R in the ij component, the rest is identity matrix. I put R prime in the ij component, and then the rest are the identity matrix, and I is not j. When I multiply them, it's rather easy to see that I get in R plus R prime at the same component. In particular, when I plug in negative R in the same component, I'm undoing what I've been doing, and I end up getting the identity matrix. The same goes through when I multiply it from the other side. In particular, I deduce that these matrices are invertible with entries inside this ring. The same is true for swapping, of course. So all these matrices that we are using are invertible matrices. The group generated by these matrices we denote by, so if I just use the elementary matrices, so these are called elementary matrices, we denote it by EL sub n. And if also permutations, if the permutations are also involved, we denote it with E sub Ln plus minus R. Okay, so now this discussion, the whole discussion shows us the following result, that we can go from A to A prime using the row and column reduction process if and only if A prime can be written as U times A times V for some U in the group generated by the elementary matrices and this swapping, these permutations, and V is also generated by the elementary matrices and swappings, but different sizes. And we say A is in relation with A prime if we can go from A to A prime using these row and column reduction process, and which is equivalent to say that I can write down A prime as U times A times V for some element, for some U inside E sub Lm, E L sub m sub plus minus R, or V and V inside this subgroup. Okay, so far we have a sort of understanding of this row and column reduction operations, and we define this kind of relation between two matrices. We say I can go from one to another using this row and column reduction process or not. And we point out that this is a kind of equivalence relation. This is an equivalence relation between these rectangular shaped matrices. Let's see why this is the case. In fact, we can relax this a bit as well, but we can change this to any subgroup and still we end up getting an equivalence relation, but let's prove it in this particular case. we need to show that every element is in relation to itself. That means it's reflexive. For that, I just choose identity on both sides, and then we get the desired equation. I need to show it's symmetric, that if A1 is in equivalence relation to A2, then A2 is in equivalence relation to A1. I just multiply by the inverse of U and V, and notice that the involved choices are groups, and therefore their inverses are also inside the same group. So we get the desired equality. So we get the symmetric relation. We get that this relation is symmetric. And finally, we have to show that this is a transitive relation. And if you think about it in terms of the row and column reduction process, it is also immediate. I can go from A1 to A2. I can go from A2 to A3 using this row and column reduction process. So I can go from A1 to A3. But we can also use this description in terms of multiplication by matrices inside these groups. So let's say A1 is in relation with A2, means that A2 is of this form. A2 is in relation with A3 means this. Now I can plug in UA1V for A2 and get the desired equality. Notice that these guys are inside these groups because these are closed under multiplication, and we get the desired equality. Okay, so far we have recalled the operations involved in the row and column reduction process in the Gauss-Jordan elimination process. And we indicated that this is an equivalence relation. We can undo what we have done. That's essentially what we are saying. But let's also recall what it is. I mean, what was the goal of this row and column reduction process? It seems that my share screen stopped working. So let me stop it for a second and then, Okay, so now let's recall what does this reduction refers to? The whole point, I mean, this elimination refers to, or reduction refers to. So the whole point of this process is to get to a simpler form. The goal is to find, quote unquote, a simplest form of a matrix A in this equivalence class. We want to use this process to get as sparse as possible, a matrix that is as sparse as possible with the most number of zeros as possible. So that's the goal of this process. Let's recall how we did it when we were working with complex numbers, let's say. So in the case of complex numbers, if the matrix is the zero matrix, we are done. Otherwise, by swapping rows and columns, I can make sure that the 1, 1 component is not zero. When the 1, 1 component is not zero, I can make use of it and get rid of all the other entries in the first row and in the first column by multiplying the ith row by negative of a sub 1 a sub divided by a1 1. So that way I multiply by this quantity and then add it to the ith row. That way I can get rid of the I1 component. Similarly, I can do this for the columns, and altogether we get that all the entries on the first row except the 1, 1, and all the entries on the first column except the 1, 1 position are 0. Now, if you think about it, the key point where we use the fact that it's complex numbers, or rather field, is the fact that if A11 is not 0, then I can solve this equation or this equation inside my ring. So if a sub 1, 1 is not 0, then it's a unit, then every such equation has a solution. So this is the key result that we are using in this process over here. And let me also point out that we continue this process with this block B, and continuing this process with the block B, we end up getting a diagonal over here, and the rest of the matrix is simply 0. So this is a kind of simplest form that we can hope for, and we end up getting such a matrix from which we can easily understand what the image of this matrix is and what the kernel is and so on. We can solve system of equations by following up this process. But again, let me emphasize that the key thing is this division, that if A11 is not 0 in a field, then I can divide by A11 and solve this equation. Now, this brings us to the Euclidean domain case. In a Euclidean domain, not every non-zero element is a unit, so I cannot necessarily solve this one, but I also have a division process. Maybe I cannot divide by this, but and get an element inside the ring, but I might have some remainder. So I can divide and subtract and get a remainder and continue this process. At some point, I get the GCD out, and then I can cancel it out. So that's the hope, that's the idea, and that's what we want to do. So by repeating the division process, we end up getting the GCD, and then this guy divides the other side, and I can cancel it out. So that's why, that is our hope, and in fact it works, and that's how we want to end up getting a matrix of this form in the same equivalence class. Okay, so let's make it formal. Here is a formal formulation of what we want to do. So suppose D is a Euclidean domain, and I give you a matrix that's not 0. If it's 0, then I'm done. It's rather silly. Now I want to use this row and column reduction process and find another equivalence, find a matrix that is equivalent to A, and A prime is of this form, some D1, and the rest of the components in the first row and the first column are supposed to be 0. Moreover, I want to make sure that D1 divides the entire entries of A prime. So every other entry, every other component of the matrix A prime is a multiple of D1. So that's my goal. So I want to kind of find the smallest, in the sense of divisibility, entry among the matrices that are equivalent to A, and put it in the 1, 1 component, and make sure that the rest of the entries in the first column and row are 0. Notice that if I manage to do this, then I can repeat the same argument for the block over here and continue like that and get exactly the same type of diagonal matrix and zeros in the rest as we did in the case of fields or complex numbers. Okay, so let's see how we can prove this proposition. Again, the idea is that I want to take the smallest possible entry and put it in the 1, 1 position among all the matrices that are equivalent with A. So among all, so let's actually formulate it. Among all the matrices that are equivalent with A and have their 1, 1 component to be non-zero, I look at all those matrices and I ask myself which one has the smallest 1, 1 component. Remember, in a Euclidean domain, we have this type norm function that can help us to measure how large elements are. So we are looking at some matrix that's equivalent to A with a non-zero 1, 1 component and smallest possible among such matrices. So we take the minimum of those norms, we call them n naught, we choose one matrix A prime that is equivalent to A, which has this property that the 1, 1 component has this minimum norm. Now, my claim is A1, 1 prime for this matrix should divide the rest of the entries in the first row and the first column. If it is not the case, I'm going to divide out, get a remainder, swap it and put it back in the 1, 1 component and get a contradiction. Okay, so let's actually write down the proof. So the claim is that 1, 1 prime, this 1, 1 component should divide 1j component and should divide I1 component. Okay, so I have to show that the remainders are 0. So I take 1j prime, divide out by 1, 1 prime, get a quotient and a remainder. Being a remainder means norm of r sub j is strictly less than norm of 1, 1 prime. Now I'm going to apply this column reduction process and subtract a sub j prime multiple of 1, 1 from the jth column. So doing this, I get, what do I get in the 1j entry? In the 1j entry, I end up getting r sub j because this minus this is r sub j. Now I can swap and put r sub j in the 1, 1 component. So I swap the first column and the jth column and end up getting a matrix that is equivalent to A and has r sub j as its 1, 1 component. If this remainder is not 0, I get a contradiction because I get a matrix that is equivalent to A and smaller norm in its 1, 1 entry, smaller than the minimum that we have chosen. So that would be a contradiction. That means r sub j cannot be non-zero. R sub j should be 0, and that means that A1, 1 prime should divide A sub A sub 1j prime. Similarly, I can argue that A sub 1, 1 prime should divide A sub I1 prime. So that exactly gives us the claim that we want. Now that we have this claim, I can apply the same argument as over here without swapping and get rid of all non-zero entries in the first row and the first column. I can just divide out, the remainder is 0, and we cancel out, and we get that all of those are 0. And notice that I'm not changing the 1, 1 component, so we get this claim that there is a matrix that's equivalent with the initial matrix A, and it is of the form A1, zeros in the rest, and norm of D1 is the minimum that we have chosen. And by claim 1, we have already proved that these are all multiples of 1, 1 entry. So we can just use the row and column reduction process and get rid of the non-zero entries in the first row and the first column. So far, so good. Now, the only remaining thing is to show that, in fact, this D1 divides all the entries of this matrix. So suppose that this is not the case. Suppose that D1 does not divide. So again, this is what we want to show, that if A prime is equivalent to A double prime is equivalent to A, it is of this form, and norm of the top one is the minimum, then this top one should divide all the rest. Suppose that this is not the case and D1 does not divide the ij entry. Similar as before, we are going to divide out by D1. But first, I need to bring it in the same row or the same column as D1 in order to be able to divide out and use the same process as before. So the first thing that I do, I'm going to look at the I plus 1th row. So this is the ij entry of B. So that would be the I plus 1j plus 1 entry of A double prime. So the first thing that I'm going to do is that I'm going to take the I plus 1th row of A double prime and then add it to the first row. So by adding to the first row, now the new first row would be this. But still, I'm in the same equivalence class as A. Now I'm going to divide D1 by, I'm going to divide B sub, the J plus 1 entry of this by D1. I can divide that guy, and so I get some remainder, but here the contrary assumption says that this is not 0, and it's remainder, so it has norm less than D1. And then I do this column reduction operation and subtract negative q multiple of the first column from the j plus 1. So I end up getting r in the j plus 1 entry of the first row. Now I can swap and put this r in the first 1, 1 component. So by swapping, I end up getting that I get a matrix that is equivalent to A, and its 1, 1 entry is R, and R has this norm strictly less than norm of D1, but norm of D1 was supposed to be the minimum amongst all such things, and that gives us a contradiction. So altogether, we end up getting this proposition that I can use the row and column reduction process, find a matrix that is equivalent to A, and the first row is D1, zeros in the rest, and zeros in the rest of the column, and D1 divides all the rest of the entries of this matrix. This is what we proved. Now I can repeat this process for the block B, and I can repeat this process for the block B, and we end up getting this form, that if D is a Euclidean domain, whenever I give you a matrix, a rectangular shape, non-zero, then A is equivalent to a diagonal form. Now my claim is that this diagonal form, DIs are going to divide one after another. D1 is going to divide D2, and D2 is going to divide D3, and so on. And my claim is that this, this moreover part we get back to later, but let's see how we can repeat by repeated application of the previous proposition, we can get this statement. Let's see how we can get that. We come back to this moreover part and discuss it later. So the moreover part tells me that this D1 is in fact the GCD of all the entries of A, is the ideal generated by all the entries of the matrix capital A. We'll come back to this moreover part later. But let's say that by the proposition that we have already proved that we can find some A prime, where A prime is of the form D1 and zeros in the first row and the column, and D1 divides the rest of the entries. Now I'm going to repeat this for B, and then I find another matrix where so I apply for B bar and then multiply the whole thing by D1. So B bar, by the induction hypothesis, is of the form, is equivalent to this diagonal guy, and 0 for the rest of the entries, where D2 bar divides D3 bar and so on. Now, if I multiply D1 by all the involved matrices during this process of row reduction and column reduction, the same process works through. So multiplying by D1 commutes with these matrix multiplications. So multiplying by D1 is in the center of matrix multiplications. So I can do that. That means that A prime would be in the same equivalence class with, so this D1 we do not touch. We see that when I do this row and column reduction process, because all these entries are 0, when I apply the row and reduction process for the rest of these columns, I'm not changing this part of the matrix of A prime. Similarly, I'm not changing this part of the matrix of A prime because all of them are 0. When I'm swapping or when I'm adding some multiple of one of these things to another one, I will end up again getting 0. So these parts do not change. So I can patch them together and get some operations, row and column reduction operations for A prime, from which we get a matrix of this form. So the first row and the first column do not change. And for the rest of the blocks, we get this one times D1. So we get this type of matrix. And that's exactly the same type as we were looking for, because D1 divides D1 times D2 bar. D1 times D2 bar divides the next one and the next one and the next one. So we get a diagonal form where each one divides the next one, and this matrix at the end is in the same equivalence class as A. Now the final part that I want to argue is this part, but it's a good idea to stop at this point. We'll continue in the next lecture.